Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in Chapter 8. In the figure, the numerical values are m1 equal to 10 kilograms, m2 equal to 1.8 kilograms, and theta equal to 32 degrees. The strings and the pulley have ignorable masses. The system is released from rest and starts to move. There is a kinetic friction between m1 and the inclined surface, determined by mu k equal to 0.28. When the mass m2 rises a distance of 10 centimeters, calculate the total kinetic energy of the system. In order to solve the problem, it is convenient and enough to draw the free body diagram of mass m1. We choose the appropriate coordinate axis as follows. We represent mass m1 by a big dot. After that, we draw all the forces acting on the body. The gravitational force acting on the body is a downward force of magnitude m1 times g. Here, it is important to decompose this force on the x and y axis. Because there is a contact between mass m1 and the inclined surface, we draw the normal force perpendicular to the surface as follows. Mass m1 goes down along the inclined surface. Therefore, the kinetic frictional force acting on the body is drawn upward along the inclined surface. As the final step to draw the free body diagram of mass m1, we draw the acceleration vector like this. Now, we can write the equation of motion by the help of the Newton's second law F net equals m times a. Because there is no motion along the y-axis, we have the net force on this axis as n1 minus m1g cosine theta equal to 0. Therefore, the normal force becomes m1g times cosine theta. The kinetic friction force has the expression Fk equals mu k times m1. As a result, we obtain Fk equals mu k times m1g times cosine theta. Okay, that's all about the free body diagram and equation of motion for m1. Now, we can write the conservation of total energy as the following. The sum of the initial kinetic and potential energies of mass m1 plus the sum of the initial kinetic and potential energies of mass m2, which is equal to the final total energy of mass m1, where ETH is the thermal energy due to friction. That is equal to the absolute value of the work done by the frictional force. Namely, the absolute value of the Fk dot H2. We can write the dot product as follows. Since cosine of angle 180 degrees is negative 1 and absolute value of negative 1 is positive 1, therefore we obtain the thermal energy due to friction as Fk times H2. Finally, we add the final total energy of mass m2 to the right. Because the system is initially held rest, the initial kinetic energies of the masses are 0. If we choose the initial position of mass m1 as a 0 gravitational potential energy level, therefore the initial potential energy of mass m1 becomes 0. And independently of mass m1, If we choose the initial position of mass m2 as a zero gravitational potential energy level for mass m2, the initial potential energy of mass m2 becomes 0. As you see, the total energy is 0. So, the final potential energy of mass m1 is negative m1 times g times h1, since it is h1 below the zero potential energy level. Next, independently of mass m1, the final potential energy of mass m2 is m2 times g times h2, because it is h2 above the zero gravitational potential energy level. Finally, the thermal energy due to friction between m1 and the inclined surface is Fk times h2. If we rearrange this conservation of total energy, we obtain 0 equals the final total kinetic energy of the system minus m1 times g times h2 times sine theta, since h1 is h2 times sine theta from the figure, plus m2 times g times h2, plus mu k times m1 times g times cosine theta times h2, since Fk equals mu k times m1 times g times cosine theta from the equation of motion. Finally, a simple rearrangement gives us the final total kinetic energy is g times h2 times m1 times sine theta minus m2 minus mu k times m1 times cosine theta. Now we put the corresponding numerical values into this equation. As a result, we calculate the final total kinetic energy of the system as 1.1 joules. Okay, that's all about this problem. Thank you for your attention. See you in the next video.